I want to do some rigid body kinetics problems. These are from Chapter 5A in Merriman Craig and Chapter 17 from Hibbler. And these problems are challenging conceptually mostly. The calculations are not so bad, but these are the type of problems that often prove difficult to visualize. And I thought it would be useful to do these three cases. So I'm going to look at some conceptually difficult problems. Think as I'm doing all of this, and again, with problems and with lectures like this, the goal is really to get you to do the work separately. So I've done all of the work, I've given you all the numbers, but try it out on your own. See if you can do the same thing and get the same result. Hopefully I got the right answers. I have here a ring gear, and a ring gear has a center gear, 3 planet gears, and an outer ring gear right here. So it's a sun and planet gears. A couple is applied of 2,000 Newton meters to the sun gear. And the sun gear is that center one where everything orbits. What is the latter's angular acceleration? So you're given r of 0.2 meters, little r of 0.5 meters, and the distance from the center to the outer ring is r plus 2 little r. This thing is fixed in place, so this outer ring is not going to rotate. You have the sun, planet gears. The mass of the sun gear is 40 kilograms. The mass of each of the planet gears is given as 370 kilograms. IS of the sun, the moment of inertia of the sun gear, is 0.7 kilogram meter squared. The moment of inertia of the planet gears is given as 40 kilograms meter squared. You're applying this 2,000 Newton meter moment about the sun gear, and you can see that it is counterclockwise, so it's a positive value. You have the sun gear here with the outer radius. You have the forces that are applied from each of the planet gears, as you can see, and you have the moment that's applied of 2,000 Newton meters. So I'm going to, and I should have put this in here, I'm going to put in assume again counterclockwise is positive and my x, y directions. And so I have the moment which is positive, and all of the planet gears have a force that's opposing motion, so it's 3F times r, and the moment of inertia times the angular acceleration of the gear. If I then look at the planet gears, I have the center of the gear. I can define here a normal and tangential system from there, a radial coordinate. I have the forces acting on this. I have sum of moments about C, which is just going to be G times R, because it is causing a counterclockwise moment, and F times R, which is causing a clockwise moment, and therefore is going to be negative. Now I planet, alpha planet. The forces, the force balance in the tangential direction, is they're both in the same direction as F plus G equals MP ACT. And, MP, mass of the planet gear. ACT is just the tangential acceleration of that planet gear. Acceleration of tangential is just going to be minus R alpha P. This is rolling without slip. At the contact point between the two, this orange point over here, minus R alpha S equals twice alpha P RP. They both have to have the same linear velocity. We've talked about that in that rotational kinematics lecture in the previous set last week or so. 5 equations, 5 unknowns, and you'll find out that the alpha of the sun gear is equal to 12.1 rads per second squared. The second one I want to look at is this one, and this is a typical case. I have a ground over here. This is probably not a good idea to have it the same color, but this is the ground. This is the rod. It's sort of here, so the ground is there. It's at a weird angle. I just chose it 57 degrees, and its length is 1 meter. 3.2 kilos is the bar. It's released from rest in the position shown. Determine its angular acceleration under 2 cases. 1, the surface is rough and the bar doesn't slip, so the bar stays fixed at that position. And the second one, which is interesting too, is the surface is smooth. So I'm going to define my coordinate system. Good for me. This time I did. Acceleration x, acceleration y, and alpha over here. And I'm going to look at the first case. And so the first case, I've got normals acting upwards and I've got weight acting downward. That's it. That's the complexity of this problem. It's interesting because it's hard to visualize. Again, the previous one and this one, very hard to visualize. Sum of moments about point C down at the ground, mg L over 2 cos theta equals 1/3 ml squared alpha. And that's a moment of inertia of a long slender rod at one point. Alpha is then calculated as 3g over 2L cos theta, so it doesn't depend on mass. And I get alpha, which is equal to 8 rads per second squared, and it's counterclockwise, which kind of makes sense. It's sort of what I expect. I give you the answer before I did the problem, but sum of moments about g and L over 2 cos theta equals 1/12 ml squared. So now we're going to go about the center of mass. Same free body diagram, but I'm going to have 4 unknowns out of this. And that's going to be the sum of forces in the x direction is equal to 0, mass times acceleration x is 0. Sum of forces in y is just n minus mg, and mass times acceleration y. And we also note that the y acceleration at point C is going to be 0. So acceleration of c is equal to 0 in the y direction, and that really should be acceleration of c in the y direction, not necessarily in the x, equals acceleration y plus acceleration of c with respect to y. So this is all with respect to the center of mass. So that becomes acceleration y plus alpha L over 2 cos theta equals 0. And from this, I've got 1, 2, 3, 4 equations, 4 unknowns. I have another relationship that's going to come about. It's a big difference in terms of what I calculate, 6g cos theta over L times the quantity 1 plus 3 cosine squared theta. But the actual sort of computation, not so difficult. Visualization of this is really hard. And I get a significantly different number, 16.96 rads per second squared, about double what I had in the previous part when there was a rough surface. So I have a rod that simultaneously is going to be able to move and rotate. So that's kind of interesting. I have here a slide that now it's about pulleys, and you love pulleys. I have a pulley that or a system that consists of 2 pulleys, one here, one there, and a crate. The pulleys are identical with a mass of 4.7 kilograms and a moment of inertia of 0.03 kilogram meters squared. A force is applied at 70 newtons right here. What is the acceleration of the crate at point A? And that's the crate right here. So how do I do this? Same thing, basically. Good for me. I've put in a system or a coordinate system. I forgot to put my rotation, but I'll deal with that in a second. I have free body diagrams of pulley 1, T and T2, T1, and MPG. So I'll have same thing for pulley 2, different forces, but same sort of diagram. And finally, I have the free body diagram of crate A, which is going to be T3 and MAG. So I have the 2 tension forces on either side. I have the weight force acting downward, and I have the common sort of tension force between the first body and the second one. So between 1 and 2, and 2 and A. And if I put all the numbers together and use the coordinate system I have there, T2 plus T minus T1 minus MPG equals MPA1. Do the same thing for all the other terms. T4 plus T1 minus T3 minus MPG equals MPA2. T3 minus MAG equals MA acceleration A. Great, no problem. So what happens next? I have to look at the moments. And as usual, I have forgotten to put in part of my diagram, but there it is. And so it's positive sort of in the counterclockwise direction as sort of convention. So TR minus T2R equals I alpha 1. For pulley 2, T1R minus T4R equals I alpha 2. So there we go. That's everything. There's no moments about the crate because there's nothing sort of going through anything but the center of mass. From the kinematics, I can say the acceleration of pulley 1 is equal to r alpha 1, acceleration of pulley 2 is equal to r alpha 2, r being the radius of the pulleys. A1 is equal to twice A2, and acceleration of A equals acceleration of 2. Substituting on all the terms, and for this, I'll admit I solved this. I could have done it any number of different ways, but because I was kind of curious about how it worked, I used SMath Desktop. And so I was able to solve the whole thing right away. Acceleration of A equals 1.94 meters per second squared. Acceleration of 2 equals 0.97 meters per second squared. If you're curious, the rest of the terms are here. Alpha 1, alpha 2, 19.4, 9.7 respectively. T1 equals 80.7. T2 equals 64.2. T3 equals 107.8. T4 equals 77.7 newtons. These are challenging conceptually. These are problems that I kind of like because they have a lot of meat to them, and you got to think really hard when you do them. It looks easy when they're done for you, so I kind of encourage you to spend the time to do them on your own, just to be comfortable with what is expected here. It's not that bad, but they often are surprisingly difficult for what they are. Thank you very much, and we'll talk again.